Pisa, the year 1240. The city council records a decree granting an annual payment to a man it calls the discreet and learned Master Leonardo, in thanks for his counsel and his teaching in matters of calculation. It is one of the only official records of his life that survives. Almost everything else, his face, his voice, his grave, has vanished. And yet the way of writing numbers that he studied across the Mediterranean and spent his life teaching surrounds you at this moment, across screens and ledgers, and on countless clock faces in countless quiet rooms. Tonight we follow Leonardo of Pisa, the man later centuries renamed Fibonacci, from a customs house on the North African coast to the court of an emperor, and then into a quiet so deep that history itself loses sight of him. So settle in, and let the day loosen its grip. We begin on the docks of a Mediterranean harbour, where a boy is watching men count. Around the year 1170, Pisa was one of the wealthiest and most powerful trading cities of the western Mediterranean, and it smelled of salt, tar, and money. It sat a few miles inland on the river Arno, in the region we now call Tuscany, and the river was its lifeline. Ships came up from the sea with their sails folded, riding low in the water, heavy with pepper from the east, leather from North Africa, silk that had crossed more borders than most men ever would. On the docks, porters shouted, ropes creaked, and somewhere beneath all of it, quieter than the gulls, was the sound that actually held the city together, the sound of counting. Pisa governed itself to an extraordinary degree. It lived, formally, within the great political web of the medieval world, with its emperors and bishops and rival cities, but its daily affairs answered to its own councils, its own magistrates, and above all to its own merchants. Along with Venice and Genoa, it was one of the great maritime republics, and it guarded that position jealously. Its war galleys had fought in distant harbours. Its trading colonies dotted the coasts of Africa and the Middle East, and at home, the city was spending its wealth on stone. In the year 1173, workers laid the foundation of a new bell tower beside the cathedral, a tower that began to lean before they had even finished it, though no one that day could have known it would still be leaning, and still be famous for leaning. More than 800 years later, somewhere in this city, in one of these years, a boy was born who would help change the way the Western world writes numbers. We do not know the exact year of his birth. Historians generally place it around 1170, but no record names the day, and no portrait made in his lifetime survives. The statues and pictures of him that exist today were made centuries later, from imagination. What we know of him comes mostly from a few sentences he wrote about himself, and from scattered official papers. Out of those fragments, patiently, a life can be assembled, and the life is remarkable. His name was Leonardo. His family seems to have been connected to a man called Bonacci, and long after his death, that connection was drawn into the single name the whole world now uses, Fibonacci. Usually explained as a contraction of the Latin for son of Bonacci, there is no evidence that he ever used or knew that name. In his own city, he was Leonardo of Pisa, a merchant's son. His father was called Guglielmo, and Guglielmo was the kind of man Pisa produced in quantity. A practical man, a man of ledgers and cargo manifests, trusted enough by the Republic to be sent abroad on its business. Merchants' sons in that city grew up among bales and barrels. They learned the weight of a coin before they learned to write. Commerce was the family trade of the whole Republic, and the boy was born directly into its machinery. Yet there was a curious weakness folded into the heart of all this wealth, one so old and so familiar that few people in Europe thought of it as a weakness at all. It was the way the counting was written down. Europe in the 12th century still kept its records mostly in Roman numerals, the letters inherited from an empire that had fallen 7 centuries earlier. The letter I for 1, V for 5, X for 10, C for 100, M for 1,000, for carving a date into stone, or recording a sum in a charter. The system served well enough, and generations of capable clerks worked within it. Its real limitation was quieter. The numerals were labels rather than instruments. They could state an amount, but they gave little help with the work of calculation itself, because they had no place value, no way for a symbol's position to carry meaning, and so the arithmetic had to happen somewhere else. That somewhere else was the counting board. Across Europe, serious calculation was done on boards and abacuses, tables marked with lines where a skilled reckoner slid counters back and forth, each line standing for ones, tenths, hundreds. A good abacus man was fast, and watching one work was like watching a musician. His fingers flickered, counters clicked, and an answer appeared. The method was trusted, and it deserved trust, for it had balanced the books of kingdoms, but it had one built in shadow. Unless every intermediate step was separately written out, the board itself preserved no trail of how a result had been reached. The counters were swept clear for the next customer, and the calculation lived only in the answer it left behind. Hold that image, because tonight's whole story grows out of it. A civilization of brilliant traders, spinning webs of commerce across the known sea, recording its results in numerals that could not calculate, and calculating on boards that could not remember. Meanwhile, on the southern and eastern shores of the same sea, people wrote numbers differently. In the cities of the Islamic world, scholars had long since absorbed the mathematics of India and built upon it. They used 10 symbols, including a strange and powerful mark for nothing at all. And with those 10 symbols written in columns, a person could add, subtract, multiply, and divide directly on the page, leaving a visible trail of every step. Nor was this knowledge entirely sealed away from Europe. It had crossed already, in fragments, through Muslim Spain, through scholars like the churchman Gerbert of Aurillac, who had studied the new figures long before, through Latin translations, quietly accumulating in monastic libraries. But fragments in the hands of scholars are one thing. The ordinary language of the counting house is another, and in the harbours of Italy, the counting house still spoke in counters and Roman letters. It is one of history's quieter ironies that among the strongest paths between these two mathematical worlds would run not through a philosopher and not through a prince, but through the son of a customs official, a boy whose childhood left no recorded trace at all. What we can say is this: he grew up inside the machinery of trade. The rhythms of the harbour were his first education, and calculation, in some form, was part of his early schooling, as it had to be for a merchant's son. Then, at some point in his youth, his world tilted southward. Pisa maintained a trading colony on the coast of North Africa. In a busy port the Italians called BUGIA, in what is now Algeria, and Guglielmo was posted there on the Republic's business, overseeing its dealings at the customs house. He wanted his son with him. In the only autobiographical passage Leonardo ever wrote, a few lines in the introduction to his great book, he says that his father summoned him to BUGIA while he was still a boy, wishing him to be taught calculation, and that it was there he was introduced to the art of the 9 Indian figures. One sentence, written decades later, that is the doorway through which everything else in this story passes. So picture the harbour of Pisa one last time as the light goes down on this chapter. A ship is being loaded at the mouth of the Arno. Somewhere on board, between the cargo and the crew, is a boy leaving Italy behind, watching his leaning, unfinished city slide away along the riverbank. He does not know what is waiting for him in the customs house on the far shore. He only knows that the sea is wide, that his father has sent for him, and that on the other side of the water, everything, even counting, is done differently. The wind fills the sails. The coast of Africa is days away. The crossing from Pisa to the African coast took a week or more, depending on the winds, and it ended in light. BUGIA in the 12th century rose in terraces from a wide blue bay, white walls climbing a green mountainside, with the peaks of the Kabylie range standing behind it like a folded curtain. Today the city is called Béjaïa, and it sits on the coast of Algeria. 800 years ago it was a thriving port within a sophisticated commercial and scholarly world, and for a boy from Pisa it must have been overwhelming in the most complete way a place can be. New language, new faith, new food, new music, new heat. Even the light itself falls differently in North Africa, harder and cleaner than the soft river haze of the Arno. BUGIA sold many things, but Europe knew it best for one humble export: wax. The fine candle wax of its hinterland lit churches and palaces from Sicily to France, and it left the city in such quantities that the French word for candle, bougie, is simply the city's name worn smooth by centuries of use. Grain, leather, oil, and metalwork moved through the harbour beside it, and wherever goods moved, Pisan ships were waiting. Pisa kept a trading colony there, a compound of warehouses, lodgings, and offices near the port, and among its institutions was the one Guglielmo served. The customs house, the office where the colony's trade met the officials, the duties, and the paperwork of the city around it. A customs house was a building made of arithmetic. Its daily work was conversion: bales of leather into dinars, dinars into Pisan money, weights of one standard into weights of another, and in a port like BUGIA, that work happened at the meeting point of two mathematical traditions. For the Italians brought their counting boards and their Roman letters, and around them stretched a commercial world whose clerks and scholars wrote their calculations directly onto the page, in 10 small symbols, in the manner that had come west from India through the world of Islam. Leonardo was placed in the middle of that daily translation, and here his own words carry the story. His father, he tells us, wished him to master calculation, and so he was set to study the art of the 9 Indian figures. He was taught, he says, by wonderful instruction in that art, and that is all he says. The surviving passage does not tell us whether this instruction came from one teacher or from several, whether his instructors were scholars or working clerks, or what language the lessons were given in. Historians can only place his teachers somewhere within the rich mathematical culture of Islamic North Africa. Whoever they were, one master or a circle of them, their names are gone. The people who taught Leonardo this art stand in the doorway of history without faces, holding out their gift, and then stepping back into the dark. The gift itself we can describe exactly, because it is in your hands every day. 9 figures. The marks we now write as 1 through 9, and beside them a 10th mark unlike anything in the Roman tradition. A small circle standing for nothing at all. The Arabs called it cipher, meaning empty. In Latin it would become zephyrum, and from that word, worn down by time, our 0, to a mind trained on the counting board. It was a strange idea. Why write down what is not there? But the empty circle was the hinge of the whole system. It held positions open. It meant that the same 9 figures could stand for units in one column, tens in the next, hundreds in the next, with the 0 keeping guard wherever a column had nothing to report. Value came not only from the symbol, but from where the symbol stood. 2 figures could say 23. Reverse them, and they said 32. A short row of marks could hold any quantity a merchant or an astronomer would ever need, and the marks themselves could be worked, added and carried and borrowed, right there on the page, every step remaining visible when the work was done. These numerals were not invented in BUGIA, and not by Leonardo's teachers either. They were born in India, developed across centuries by mathematicians whose names are mostly lost, and they travelled westward along the roads of trade and scholarship. In the early 800s, in the scholarly world of Abbasid Baghdad, under the patronage of the Caliph al-Mamun, a Persian scholar named Muhammad ibn Musa al-Khwarizmi wrote influential works that helped systematize and transmit this knowledge, first across the Islamic world and, in time, toward Europe. One explained the Indian reckoning, the art of calculating with the 9 figures and 0. Another, a treatise on solving equations, carried in its title the Arabic phrase al-jab, and that phrase, crossing into Latin, became algebra. His own Latinized name gave rise to the word algorithm, the old term for calculating with these figures, and ultimately to our word algorithm. So when the boy from Pisa bent over his lessons in BUGIA, he was not meeting a local curiosity. He was joining a current of thought that ran from ancient India through Baghdad to the shore he stood on, centuries wide and still flowing, and something in him answered it. He tells us himself that he came to delight in the study of the 9 figures beyond all else. Notice the quiet phrase hiding in that sentence. Beyond all else. He was comparing, even as a student. He was setting the new arithmetic beside the counting board of his childhood and keeping score. Picture him. Then, in the years that follow, a young Italian in a Mediterranean port, working sums on paper, where a board calculation vanishes with a sweep of the hand, his remains, line under line, every step open to checking. In a world of merchants, that is not a philosophical advantage. That is trust. And trust is money. The customs house had taught him what the new numbers were, but BUGIA was one port, and its methods were one tradition among several in a sea full of traditions. Before he committed his life to these figures, he wanted to know what else was out there, how the reckoning was done in other harbours, under other kings, in other tongues. To learn that, he would have to go to sea. And the sea, for once in this story, is somewhere the records actually follow him. In the introduction to his great book, Leonardo gives us a single sentence about the next stretch of his life, and it opens like a map. He writes that in the course of business travels he studied the methods of calculation in Egypt, Syria, Greece, Sicily, and Provence. One sentence, 5 names, years of a working life, folded into a line of Latin. He gives no dates, no order of travel, and no stories from the road. And so tonight we will not invent any. We cannot know what he learned in each place, or even whether the list follows the sequence of his journeys. What we can do is walk the map he left us, and imagine the world through the eyes of a young man who has just discovered that his one beloved subject is far larger than the single harbour that taught it to him. Because that is the quiet drama of these years. Every port he entered widened the sky over his head. He had come out of BUGIA believing he had found the best way to count. Now he had to test that belief against the whole sea. Egypt, for a Pisan trader, meant above all the great port of Alexandria, where the grain and goods of the Nile met the shipping of 3 continents. Egypt, in this era, was among the wealthiest trading powers on earth, and its commerce ran on paper, contracts and letters of credit and warehouse receipts, kept by clerks fluent in the reckoning he had just learned to love. Imagine the quiet thrill of it for him. The method that had felt like a personal discovery in BUGIA turned out to be the ordinary working language of one of the oldest commercial civilizations in the world. He had not found a curiosity. He had found a homeland for the thing he cared about. Syria, in the language of Italian merchants, meant the commercial cities of the eastern Mediterranean coast, the ports serving Damascus, and the caravan roads running east toward Baghdad and beyond. Here the trade of the sea met the trade of the land, and here too the working mathematics of the markets was the arithmetic of the 9 figures, practised in a scholarly world with its own refinements, its own ways of arranging the work on the page. Whether Leonardo sat with any particular master in any particular city, no document says, but a young man who had crossed a sea to compare methods would have found, in these markets, exactly the differences he was hunting, small variations in how the same truth could be written. Greece, in the usage of his time, pointed to the lands of the Byzantine Empire, and perhaps to Constantinople itself, the largest Christian city in the world. This was a different inheritance altogether. Here the learning of the ancient Greeks survived in its original tongue. Euclid and Archimedes copied and recopied through the centuries. Geometry preserved like a flame that had never gone out, alongside numeral customs of the Greek world that were older than Rome's. If the reckoning of the Islamic world showed a traveller how to calculate with power and speed, the Greek inheritance held something else: the ancient art of proof, the insistence that a method be shown to be true and not merely useful, Leonardo's later books reveal a man deeply at home in that geometric tradition. Whether that particular journey planted the seed, we cannot know, but the seed was in the soil he was walking through. Sicily was the strangest and most layered stop of all. The island had been Greek, then Arab, then conquered by Norman knights, and by Leonardo's lifetime it was a kingdom where Latin, Greek, and Arabic all served as languages of government and learning. In Palermo, translators were turning Arabic science into Latin for the first generations of European readers, and Sicily touches our story at one more point. Though no one could have known it yet, in the year 1194, a child was born there who would grow up to be Frederick II, King of Sicily and Emperor, and one day, improbably, the patron whose court would come calling for a Pisan mathematician. Their paths were not ready to cross, but the island had now touched both their lives. Provence, finally, meant the coast of what is now southern France, with its ports and fairs where Italian shipping met the inland commerce of Europe. It was the Christian West again, counting boards and Roman letters again. The world of his childhood, seen now through the eyes of a man who had crossed 3 continents of arithmetic, and perhaps that was the true end of his education. He could stand in a European market at last and see it whole, its ships heavy with wealth, its ledgers written in a language that could barely calculate, and know, with the certainty of a man who had checked everywhere else, that it did not have to be this way. Somewhere in these travelling years, the comparison he had been running since BUGIA reached its verdict, and he states it in his book plainly, as a settled conviction, set beside the method of the Indian figures. He judged the other systems he had studied fell short, almost as errors by comparison, not error meaning false answers, but error meaning a poorer path. He had sailed the sea in every direction open to a merchant of his city. Nothing he found had beaten the 9 figures and the 0. By the opening years of the 13th century, Leonardo came home to Pisa. The harbour sounded the same. The counters still clicked on the boards. The Roman letters still marched across the ledgers, as if the mathematical worlds he had crossed lay on some other planet rather than across one sea. But he was carrying, in his notes and in his memory, the arithmetic of many shores, and a conviction about what ought to be done with it. What he did with it was right, and the book he wrote is one of the reasons tonight's story exists at all. The Pisa that Leonardo came home to was still building. The cathedral gleamed. The baptistry was rising beside it, and the bell tower now stood several stories tall, and already visibly, stubbornly tilted. It was a city of practical men solving practical problems, and somewhere inside it, at a desk no record describes, a merchant's son set himself a task that was practical and enormous at once. He would put everything he had learned, the figures, the methods, the applications, into a single book in Latin, the shared language of educated Europe. He finished it in the year 1202. He called it Liber Abaci, and the title needs one moment of care, because it looks like it means a book about the abacus. In the Latin of his time and place, the word could carry a wider sense, calculation itself, the art of reckoning, and whatever the title promised, the content was clear from the first page. This was not a manual for the counting board. It was a book about calculating with pen and figures, and it opened with a declaration that has been quoted ever since. These are the 9 figures of the Indians. He wrote, setting them out on the page, with these 9 figures, and with the sign Zephyrum, which the Arabs call Sifr, any number whatsoever can be written. Any number whatsoever. Europe had heard pieces of this before. The figures had appeared in Spanish monasteries, in translated treatises, in the work of a few scholars stretching back 2 centuries, but few European readers had ever seen the system laid out with such range, such clarity, and such relentless practical force as this book was about to deliver. The claim on the first page was not a curiosity being reported. It was a tool being handed over by a man who had spent his life testing it in the places where it was daily bred. The structure of the book is the structure of a good teacher's mind. First the figures themselves, and how position gives them value. Units, tens, hundreds, the 0 holding empty columns open. Then the operations: addition, subtraction, multiplication, division, each laid out step by step. With worked examples, a reader could follow line by line and then repeat with quantities of his own. Then fractions, which merchants needed constantly, because cargoes and coins rarely divide evenly. And then, chapter after chapter, the real world comes flooding in, because the heart of Liber Abaci is a merchant's working life translated into problems. How to convert between the monies of different cities, when one place reckons in one coin and another in a different coin of different fineness. How to divide the profits of a voyage among partners who invested unequal sums. How to price the mixing of metals, when silver of 2 purities is melted into 1. How to settle barter. Cloth against pepper, with no coin changing hands. Problems of interest, of discount, of shares. Problems that begin, in effect, a ship sails from Pisa with a cargo worth so much, and end with a number a real trader could carry to a real table and defend. In its modern printed editions, the book runs to some 600 pages, and most of those pages smell of the warehouse, not the study. Anyone who has studied from a good textbook would recognize the design. Definitions first, methods second, examples everywhere, difficulty rising slowly, so that a diligent reader is never asked to leap a gap, only to climb a stair. Historians of mathematics often describe it as one of the most influential works of practical arithmetic Europe ever produced, and its influence flowed exactly through that usefulness. It did not ask Europe to admire the new numbers. It showed Europe, sum by sum, what they could do, and scattered among the merchant problems, Leonardo planted puzzles, recreational problems, riddles with numbers, some drawn from older collections. The kind of exercise a teacher includes to keep a student's mind awake. A hound chasing a hare at different speeds. Men finding a purse and arguing over its division. Birds of different prices bought for a fixed sum. Little stories. Each one a lesson in disguise. One of them involved a pair of rabbits in a walled space, and we will meet it properly in the next chapter, because that small puzzle, a page in a book of hundreds, is the reason most people alive today have heard this man's name at all. In 1202, though nobody was looking at the rabbits, The book went out into a Europe that copied every text by hand, one manuscript at a time. There were no printing presses, and would be none for another 2.5 centuries. A long technical work, spread only if serious people judged it worth the labour of copying. And Liber Abaci found such people. Slowly, in the merchant cities and among the learned, Leonardo himself kept working. Other books followed, on practical geometry, on problems and their solutions. And the clearest sign of how far his reputation eventually reached is that in 1228 he prepared a revised and expanded version of Liber Abaci, and dedicated it to Michael Scott, the famous scholar and translator then serving at the court of the Emperor Frederick II, a merchant's textbook dedicated into the orbit of one of the most learned courts in Europe. The boy from the customs house had written his way to the emperor's threshold. Still, of everything the book carried, the smallest symbol may have mattered most. The zephyrum, the zero. Most Latin European bookkeeping had long operated without a working sign for nothing, and here was a book placing it before ordinary readers and showing, page after page, what it was for. Not nothing as mere absence, but nothing as information, the empty column that makes every full column meaningful. Some historians see in that little circle a quiet turning point in the Western habit of mind. The moment emptiness became something you could write down, hold steady, and calculate straight through. Night has settled over Pisa now. In our story, the manuscript is finished. The ink is drying, and on one page, among the hundreds, a pair of rabbits is waiting in a walled garden for the world to notice them. It will take the world 600 years. It will take us only until after this breath. The problem sits among the puzzles of Liber Abaci, given no special place of honour, taking up barely a page. It goes like this, and you can close your eyes and follow it, because it was built to be pictured. A man places one pair of rabbits in an enclosed space. A garden surrounded on all sides by a wall. The rules of this little world are simple. The starting pair is grown, ready to breed at once. Every pair, once it is old enough, produces one new pair each month, and every newborn pair waits 1 month to grow up before it. 2. Begins to breed. No rabbit ever dies, and none escapes. The question is, how many pairs will fill the garden at the end of 1 year? So let the months pass slowly, 1 breath each. The garden begins with the single grown pair. After the first month, they have produced a young pair, so there are 2. In the second month, the grown pair produces again, while the young pair is still growing, so there are 3. In the third month, the 2 older pairs both produce, and there are 5, then 8, then 13, then 21, 34, 55, 89, 144, 233, and at the end of the 12th month, the garden holds 377 pairs of rabbits. That is the number Leonardo himself sets down at the close of his little table. 377. If you have seen this puzzle retold in a modern book, you may have met a slightly different final figure, because some modern versions start the clock a step earlier, counting the very first pair as newborns. The garden is the same, only the labelling of the months moves. Now, listen to the numbers themselves. Without the rabbits: 1, 2, 3, 5, 8, 13, 21, 34, 55. There is a rule breathing inside them. Each number is the sum of the two before it. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. That is the entire secret. And the reason sits in plain sight inside the garden. The pairs alive next month are all the pairs alive this month, plus one new pair for every pair old enough to breed. And those breeders are exactly the pairs that were already alive the month before. This month plus last month. Forever. Leonardo solved the puzzle, recorded the answer, and moved on to the next problem. He never named the sequence. He never returned to it in his surviving work. For him, it was a teaching toy, a way of showing readers how a simple rule, applied patiently, builds a pattern, and he did not discover it. Centuries before Liber Abaci, scholars in India knew this exact sequence, and it arose there not from rabbits but from poetry. Sanskrit verse is built from short syllables and long syllables, a long one lasting twice as long as a short, and Indian scholars of prosody asked how many different rhythms could fill a line of a given length. Count the patterns, and this same sequence appears, growing by the same rule. Each count the sum of the two before. It belongs to a tradition commonly associated with scholars such as Virahanka, working well before Leonardo's birth, and Hemachandra, who set it out clearly in the century of Leonardo's own life. None of this diminishes the Pisan, who never claimed the numbers as his own. It simply means the sequence, like the numerals themselves, is older and more widely owned than the single name it ended up wearing. As for that name, Leonardo never heard anyone speak of a Fibonacci sequence, because for some 600 years, no surviving source calls it by that name. The rabbits sat in their manuscripts, copied along with everything else, read by the specialists who read such books, while the sequence itself waited, unnamed, only in the 1800s, when a French mathematician named Edouard Lucas studied these numbers deeply and needed something to call them, was the Pisan's late nickname attached to them, and we will watch that christening happen properly in a later chapter, because it belongs to the strange story of his return from obscurity. Before we leave the garden, stay one moment with the thing itself, because it is the reason this page refuses to be forgotten. The rule is almost childishly simple. Add the last two numbers. A young child can do it, and yet the sequence it produces has a mathematical depth that scholars are still mining today, and in later centuries it would be connected, sometimes carefully and sometimes carelessly, to the growth of plants, to proportion and design, to claims both wonderful and false. Sorting the true connections from the myths is a pleasure we are saving for its proper place near the end of tonight, and it is worth the wait. Simple rules, patiently applied, building something vast. That was the lesson of the rabbits. And if you look back across the story so far, it has quietly been the lesson of the man's whole life. One boy, one customs house, teachers with no names, one book, copied by hand from city to city. This month, plus last month, forever. But a book that keeps spreading eventually reaches powerful readers. And in the 1220s, one of the most unusual courts in Europe turned its attention toward Pisa, and toward the calculator living quietly inside it. The rabbits can rest now. The emperor is next. Picture a money changer's table in an Italian city. Some decades after Liber Abaci, a cloth spread over the boards, counters stacked in neat columns, a locked box, a ledger, and behind the table a man whose reputation is his entire fortune. Merchants trust him because they can watch him work. The counters sit there, physically, in full view of both parties, and when a sum is settled, everyone at the table has seen it settled. Now a younger man arrives, trained in the new reckoning, and offers to do the same work with a pen, in small foreign figures, on a page the client cannot read. The older man is not a fool for hesitating. He is guarding the one thing his business runs on: trust. Every story of a new invention has a chapter like this one, and it is usually told wrong, as a battle between genius and ignorance. The truth about the slow arrival of the new numerals is quieter and more interesting, because the resistance had reasons, and some of the reasons were good. Begin with the practical one. The new figures, in unfamiliar handwriting, were easy to misread and, more worryingly, easy to alter, especially before standardized shapes and settled bookkeeping habits had spread. A carelessly formed figure could be mistaken for another. A 0 could be slipped onto the end of a sum, and a debt of 10 could swell into a debt of 100. Counters on a board leave nothing to tamper with after the fact. Fresh ink can be changed. For men whose ledgers might be examined years later, in lawsuits, in inheritance disputes, in audits. That was not superstition. It was a professional risk assessment. There was unease of other kinds too. The 0 puzzled people. Roman numerals had no sign for nothing, and some historians describe a genuine discomfort in this period around a mark that meant absence, a something standing for nothing, an idea that felt slippery in a way the solid counters never did. The figures were foreign besides, arriving from beyond the Latin world, and novelty from abroad has rarely enjoyed a warm welcome from settled professions in any century, and the resistance eventually reached the level of law, in the most famous example of all, which deserves to be told exactly. In the year 1299, the city of Florence, then rising toward its position as a banking capital of Europe, issued a statute concerning its guild of money changers, restricting the recording of sums in their account books by means of the new figures, and requiring amounts to be written out in words instead. That much is documented. The reason is where care is needed, because the statute does not fully explain itself. The traditional reading, repeated by many historians, is fear of fraud, the alterability of the new digits. Some modern scholars read it more cautiously, as conservative bookkeeping regulation of a familiar municipal kind. Either way, the plain fact remains striking. Nearly a full century after Liber Abaci, sophisticated Florentine bankers were being officially steered away from the figures it taught. Writing sums out in words, incidentally, is a safeguard that survives to this day. On many checks that still ask for the amount in figures and again in writing, a small daily descendant of a medieval anxiety. Beyond fear, there was the heaviest force in human affairs, which is habit. Reckoning masters made their living by their speed on the board, and schools taught what the masters knew. Methods that have balanced the books of kingdoms do not surrender to a better argument overnight. And so they did not. The two ways of counting yielded to each other unevenly, coexisting for generations, each holding the tasks it did best. While the new figures spread mainly through a rising institution, the arithmetic schools of the Italian cities, the abaco schools, where boys destined for trade learned the new reckoning from textbooks in the tradition Liber Abaci had helped to found. Merchants adopted what their sons had been taught. The sons taught their own sons. The change took, by most accounts, the better part of 3 centuries, and even the printing press, arriving in the mid-1400s, only accelerated a turn that was already long underway. Leonardo saw none of that outcome. In his own lifetime, the reach of his book was real but narrow, a network of scholars, schoolmasters, and forward-looking merchants, yet within that network his name travelled, and it travelled upward, because there was one court in Europe where foreign learning was not a mark against an idea but a recommendation, one ruler who collected scholars the way other kings collected falcons, and hunted knowledge across the boundaries of language and faith. His subjects and his enemies alike called him the wonder of the world, and in the 1220s his circle turned its attention to the calculator of Pisa. Frederick II is one of the strangest figures ever to wear a European crown, and he deserves a moment of his own before he enters our mathematician's story. Born in 1194, orphaned, young, crowned King of Sicily as a small child, he grew up in Palermo, that layered island capital where Latin, Greek, and Arabic all served the government. The adult he became was unlike any monarch of his age. He spoke several languages. He wrote a treatise on falconry that modern scholars still admire for its insistence on direct observation over inherited authority. He founded a university at Naples, corresponded with Muslim rulers and scholars even while popes raged against him, and gathered around himself a court of learned men from across the Mediterranean world. Contemporaries reached for a phrase that has stuck to him ever since: stupor mundi, the wonder of the world. In that circle of court scholars stood Michael Scott, the Scottish translator and philosopher to whom Leonardo dedicated the revised Liber Abaci, and a figure named Johannes of Palermo, a scholar of the emperor's entourage with a taste for hard problems. This was the world that heard of the Pisan calculator, and Leonardo himself, in the openings of his later works, tells us what happened, which means this part of the story rests on his own words. The emperor's court took notice of him around the year 1225, when Frederick's travels brought him to Pisa. Leonardo was presented to the emperor, and in connection with that meeting, Johannes of Palermo set him mathematical problems, in the manner of a challenge, the kind of test by which learned reputations were examined in that world. We do not know the room. We do not know whether the emperor watched the working or only received the results, and no chronicle stages the scene for us. So, tonight, neither will we. What survives is better than a scene. What survives are the problems themselves, with Leonardo's solutions, published in his own books, and they are worth meeting slowly, without a single written equation, because you can feel their difficulty even in plain words. The first problem asked for a number of a very particular kind. Find a quantity such that if you square it and add 5, the result is a perfect square, and if you square it and subtract 5, the result is also a perfect square. Both directions at once. Adding 5 must land on a square, and removing 5 must land on a square. Whole numbers refuse to cooperate, and almost every fraction fails too. Leonardo found the answer, the fraction 41/12, and showed that it works. More than that, in a book we will visit properly in the next chapter, he mapped the entire landscape such problems live in, so that his answer stands not as a lucky find, but as one house in a city he had surveyed street by street. The second problem was crueler. It asked for the solution of a particular cubic equation, a problem involving an unknown quantity multiplied by itself and then by itself again. What Leonardo did with it has been admired for 8 centuries, in 2 movements. First, he argued that the answer could not be any of the tidy kinds of number, his mathematical inheritance considered exact. Not a whole number, not a simple fraction, not any of the lengths that ruler and compass geometry could construct in the classical manner. The true answer lay beyond those categories. And then, instead of stopping at that boundary, he produced an approximation, expressed in the astronomer's fashion of the age, in 60ths and 60ths of 60ths. And when his value is converted into modern decimal form, it is accurate to roughly 9 decimal places. 9 decimal places, worked by hand, by lamplight, in an age when modern algebraic notation did not yet exist, and every step of the reasoning had to be carried in words and in the reckoner's own conventions. Historians of mathematics have often described this computation as unmatched in Latin Europe for centuries afterward. Sit with that a moment. At the pace of this quiet hour, a man answers a question so precisely that, by many accounts, the Latin world took centuries to clearly better his answer. And notice what the whole episode means, standing where it does in his life. The merchant cities of his own world had been slow to trust the new reckoning, hedging it with statutes and habits. The most powerful ruler in the Western world, presiding over one of the most cosmopolitan courts of the age, tested the Pisan and found him worth honouring. Books followed from Leonardo's pen in these years, addressed into that court, including a work sent to the emperor himself containing what Leonardo called the flowers of his solutions. The son of a customs official, with no university and no title, had been examined at the summit of European power on the strength of pure calculation, and had passed. One of the books born from that court connection is his masterpiece, the deepest mathematics he ever wrote, a work that would wait 400 years for a mind fully ready to answer it. It is called the Book of Squares, and it is where our story goes next. In the year 1225, the same year his path crossed the emperor's, Leonardo finished the work that mathematicians now often regard as his masterpiece. He called it Liber Quadratorum, the Book of Squares, and he dedicated it to Frederick himself. It is a shorter book than Liber Abaci, and a stranger one. The great textbook had been written for the counting table, full of cargoes and currencies and things a man could touch. The Book of Squares serves no market at all. It exists because a question caught fire in one man's mind, and he followed it as far as his century allowed, and then a little farther. The question grows out of the challenge problem from the court, the search for a number whose square, +5 and -5, lands on perfect squares both times. To answer it properly, Leonardo had to understand square numbers from the inside. So before we follow him up, let us make sure we can see a square number the way he saw one, as a shape rather than a symbol. Picture pebbles on a table. In the dark of a quiet room, one pebble is a square, a tiny one. Add 3 pebbles around its corner, wrapping it, and you have 4 pebbles arranged 2 by 2, a perfect square. Wrap that square with 5 more along 2 of its sides, and you have 9, 3 by 3. Wrap again with 7, and you have 16, 4 by 4. Notice what the wrappings are: 3, 5, 7, 9. The odd numbers, one after another. Every square is the sum of the odd numbers in order. 1, 1 plus 3, 1 plus 3 plus 5. This was ancient knowledge, older than Rome, and Leonardo lays it near the opening of his book like a key on a table, because if squares are built by stacking odd numbers, then the distance from one square to the next is always a single odd number, and a person who understands those gaps can begin to climb between squares deliberately, the way a mason understands a wall because he understands the bricks. From that simple picture, the book ascends, proposition by proposition. Leonardo works out the deep grammar of squares, how 2 squares can combine into another square in the manner of the ancient 3, 4, 5 triangle of the rope stretchers, how to generate whole families of such triples on demand, rather than stumbling on them one at a time. And then the centerpiece, he asks when a square can be increased by some amount and decreased by the same amount and land on squares both times. And he gives the special quantities that make this possible a name of his own. Congruum. He maps their behavior, proving, among other things, that every such quantity must be divisible by 24, and showing exactly how the emperor's number 5, suitably scaled, belongs to the family. The challenge at court had not been answered by luck. It was answered because Leonardo had surveyed the entire landscape the problem lived in, and could walk to the solution like a man walking a road he had paved himself. We promised a night without equations, and the details matter less than the shape of the achievement. Here is the shape. This is number theory, the study of the whole numbers for their own sake, the oldest branch of mathematics. The ancient Greeks had worked such problems, above all Diophantus, whose writings the mathematicians of the Islamic world had translated, studied, and carried forward. Leonardo stands in that long line, and historians of mathematics often describe the Book of Squares as one of the finest works of its kind from the medieval Latin world. A peak with no obvious rival in its own time and place. The judgment usually attached to it is striking. Serious advances beyond this work, in this field, are generally dated to the 1600s. To readers of a later age, like the Frenchman Pierre de Fermat, whose questions picked up threads the Pisan had laid down some 4 centuries earlier. 4 centuries. Sit with that measure of solitude for a moment. It suggests that when Leonardo set down his pen in 1225, he had written past the horizon of his own era, a letter addressed to readers who did not yet exist. He seems to have known the value of what he had done. In his dedication to the emperor, he offers the work with quiet confidence, as the flower of his art, and in the writings of these court years, there survives one small, tantalizing human detail. In one of them, Leonardo refers to himself with a curious extra name, Bigollo. Scholars have puzzled over the word ever since. In the dialects of the time, it may have meant a traveller, a wanderer, which would suit his biography perfectly. Others have read into it a self-mocking shade, something like the idler, the good-for-nothing. It is tempting to hear humour in it. A great mind, smiling at its own strange road, though the word's exact colour is uncertain and likely to remain so. Even this, the closest thing we have to a personal note, arrives in a language we can no longer fully read. By the middle decades of his life, then, Leonardo of Pisa had rebuilt the arithmetic of commerce in one book, and touched the far frontier of pure mathematics in another. He had been examined and honoured by one of the most brilliant courts of his age. By any measure a biographer could invent, he had arrived, which is why what happens next in the record is so strange, and so quietly haunting, because what happens next is almost nothing at all. Every life in this series ends, but few end like this. There is no deathbed scene in this chapter, no last words, no funeral. There is a single sheet of administrative writing, and then a stillness so complete that it has become part of the story itself. The document is the one we met at the very start of tonight. In the year 1240, the commune of Pisa recorded a decree concerning a man it calls the discreet and learned Master Leonardo. The city granted him an annual payment of £20 plus customary allowances, and the decree states why: for his services to the city and its citizens, given through his counsel and his teaching in matters of accounting and calculation. Behind the formal Latin you can just make out a living man. The Republic's officials had evidently been coming to him, perhaps for years, with the mathematics of the state, valuation, audits, the tangled arithmetic of a trading city, and he had served, and taught, and the city judged that such a man should be recognized and retained. Reading it with modern eyes, it is hard not to see something like a pension for a public treasure, the city keeping its mathematician, though those are our words, our categories, laid gently over a 13th century document that says only what it says, and that is the last time history sees him alive. After the decree, the record simply stops. We do not know when Leonardo died. Historians commonly write that he died sometime after 1240, perhaps within a decade, and every word in that sentence, perhaps, sometime, is doing honest work. No chronicle mentions his passing, no grave is known. If that seems shocking, remember what the 13th century kept records of, and for whom chronicles followed wars, popes, emperors, famine. A retired calculator, however learned, died the way almost everyone died then, locally, privately. Noted, if at all, in books of parish and family that time has since eaten. The darkness around his death is not a dramatic mystery. It is the ordinary darkness of the Middle Ages, closing over one more life. The stranger silence is the one that followed, and it is the true subject of this chapter, because it was not only the man who faded, it was the name. The mathematics itself survived and spread. That must be said clearly. His textbook stood near the head of a tradition of practical arithmetic that flowed into the abaco schools of the Italian cities. where generations of merchants' sons learned the new reckoning, and through that broad current, alongside other channels and other books, the figures conquered the ledgers of Europe. The victory he had worked for arrived in full, but victories detach from the people who prepare them. The clerks of the 1400s, writing their accounts in the new figures, did not know they were completing a project a Pisan had laboured at. The knowledge became anonymous, the way successful knowledge always does. No one thanks an inventor each time they strike a match. His deepest work fared worse. The Book of Squares slipped almost entirely out of circulation, surviving into the modern world through an exceptionally narrow manuscript tradition, centred on a single copy that came down through the centuries. One fire, one flood, one careless clearing of a shelf, and the finest surviving mathematics of the medieval Latin world would simply not exist for us. And tonight's story would have a hole in its heart that nothing could fill. There is a strange justice in all this. If you turn it in the light, Leonardo's gift had been to make difficult things usable, to take the mathematics of distant scholars and hand it on so smoothly that it stopped feeling like anyone's invention. The more completely a tool is adopted, the less anyone remembers adopting it. His obscurity was, in a real sense, a measure of his success, though we should let that stand as an image rather than a verdict, because chance and the long centuries played their part as well. So let him rest where the documents leave him, an old master in Pisa, honoured by his city, consulted on its accounts, the sea trade rumbling on below, the bell tower still rising and still leaning, its builders still arguing. Somewhere beyond the decree there was a last calculation, a last lesson, a last evening. History does not hold those scenes, and we will not stage them. What history does hold is this: 6 centuries after the Pisan silence began, in the libraries of a very different Europe, scholars would begin pulling at the thin threads he left behind. A Roman prince would spend his fortune printing the surviving works he could recover, and a French mathematician, studying a little staircase of numbers climbing out of a rabbit puzzle, would need a name for it, and would reach back across 600 years, and choose his. The man has disappeared. The name is about to be born. Between the death of Leonardo of Pisa and the birth of his fame lie 600 years, and history offers few stranger journeys than the one his work now took, a journey whose hero is not a person but a stack of parchment, sleeping in the dark while the world changed around it. Consider what a book was in the 13th century. Not an object you bought, but an object someone made, one copy at a time, a scribe bending over a desk for months, ruining his eyes by candlelight. A long technical work, dense with figures and tables, was a mountain to copy, and only serious institutions and serious men attempted it. The survival of any medieval text is a relay race across centuries, manuscript to manuscript, library to library, and in every generation the race can be lost. Fire loses it, damp loses it, war loses it, indifference, the quietest of the destroyers, loses it most often, because a book no one values is a book no one copies, and a book no one copies has one death left in it. Leonardo's writings ran that race with mixed fortune. The practical works fared best, because usefulness is a kind of armour. Libera Bassi was copied, and copies bred copies, and its methods flowed into the Abaco tradition that taught the counting houses of Italy. His ideas spread anonymously through those schools, absorbed into a broad river of practical arithmetic fed by many springs. But his name thinned with every decade, and his deepest work nearly vanished outright. The Book of Squares, narrowing down to that single fragile thread. By the time Europe had printing presses, the man who once stood before an emperor had become little more than a name in old inventories, an author few read, because few could find him. Then, slowly, the world turned toward him again, and it turned for a particular reason. Europe in the 1800s fell in love with its own past. This was the great age of history as a discipline, of archives opened and catalogued, of scholars crawling through libraries, hunting the origins of modern things. Among the questions that mattered was one that sounds simple and is not. Where did our numbers come from? The people who asked it followed the trail backward, ledger to ledger, century to century, and the trail kept leading through the same forgotten Pisan. Two names carry this return from obscurity. The first is Guillaume Libri, an Italian-born mathematician and historian working in France. Brilliant and, it must be said plainly, notorious, for he was later disgraced in a scandal over manuscripts taken from libraries he had been trusted to inspect. History is rarely tidy about its instruments, yet it was Libri's history of the mathematical sciences in Italy, published in the 1830s, that did much to fix upon Leonardo the nickname by which the world now knows him, Fibonacci, drawn from the old phrase for son of Bonacci, a name the man himself never used. The second is Baldassare Boncompagni, a Roman prince with a scholar's soul, who devoted his private fortune to the history of mathematics. In the 1850s and 1860s, Boncompagni hunted down the manuscripts that could still be found and printed the surviving works of Leonardo of Pisa, including that lone copy of the Book of Squares. What had been sealed for 6 centuries was opened to every mathematician in Europe, and the readers Leonardo had written toward at last sat down with his book. Then came the christening. In the 1870s, the French mathematician Édouard Lucas, one of the great number theorists of his century, turned his attention to the staircase of numbers that climbs out of the rabbit puzzle. Lucas studied the sequence deeply, uncovered new properties, connected it to problems across mathematics, and used its relatives in his famous tests for whether enormous numbers are prime. A sequence this important needed a name, and Lucas called it the Fibonacci sequence, while a companion sequence he explored now carries his own name in return. He was not alone in building the sequence's modern fame, and the name Fibonacci was already in scholarly use before him. But it was in these decades, through work like his, that the rabbit numbers stepped out of an old Latin book and into the permanent vocabulary of mathematics. Notice the strange machinery of fame. The living Leonardo was honoured for his textbook and his service to Pisa. The remembered Fibonacci became famous above all for a puzzle he had treated as a toy. The name he never heard is now fixed to numbers he never claimed, and both are known to millions who could not name another medieval mathematician. Fame, it turns out, keeps its own ledger, and no one is shown the entries in advance. By the end of the 19th century, the name was secure. But the sequence itself was about to become famous far beyond mathematics, out in gardens and forests, in places no one expected numbers to live, because botanists, counting patiently, had begun to notice something in the architecture of plants. The numbers were growing on them. Take a sunflower in your mind's eye and hold it up in the last light of the day. The face of it is a dense spiral galaxy of seeds, and if you look closely, the seeds arrange themselves into two families of spirals, one family curving clockwise, one counterclockwise. Botanists have counted those spirals patiently across many studies and great numbers of flower heads, and the counts land again and again on neighbouring numbers from our staircase, 34 one way and 55 the other, or 55 and 89, not in every flower, and honest studies record the exceptions, but often enough to form a striking and reproducible pattern. Pine cones show the same signature, commonly 8 spirals against 13. Pineapples show it. This is not folklore. It is measured, published, repeatable botany, and the field that studies it. The placement of leaves and seeds and florets is called phyllotaxis. Why would a flower count? The honest answer has 2 layers. Consider first the geometry. A plant grows new elements from a central tip, each new seed or floret budding at an angle from the last. If that turning angle were a neat fraction of a full circle, a half or a third, the elements would line up into a few spokes, wasting the space between them. One especially efficient arrangement emerges near an angle that resists every neat fraction, about 137.5 degrees, which is the full circle divided according to the golden ratio. Place elements at that angle, one after another, and spiral families appear whose counts are Fibonacci numbers. The second layer is biology, the question of what steers a growing plant toward that angle. And here, scientists study how growth substances concentrate and inhibit one another at the tip, building models that reproduce the patterns well. While research on the living details continues, the flower is not doing arithmetic. It is solving a problem of growth and packing. And Fibonacci numbers are what a good solution looks like from the outside. The golden ratio itself deserves 1 slow minute, because it is the bridge between the rabbits and the roses. Walk up the staircase of the sequence and divide each number by the one before it. 3/2, 5/3, 8/5, 13/8. The answers wobble. High, low, high, low. But the wobble shrinks, closing in on a single value, about 1.618. The Greeks knew this proportion from pure geometry long before anyone connected it to the sequence. The division of a line in which the whole relates to the larger part exactly as the larger part relates to the smaller. Its appearance in the packing of seeds and leaves is genuine, well-documented science, and around that shining kernel of truth has grown one of the great myth clouds of popular culture. This channel promised you the difference between the two, and here it is. You have likely heard that the Parthenon in Athens was designed around the golden ratio. Historians of architecture have looked hard for evidence, and there is none in the ancient sources. The claim appears more than 2,000 years after the temple was built, and the measurements only fit if you choose, generously, where to place your rectangle. You have likely heard that Leonardo da Vinci painted the Mona Lisa by golden proportions. The painter left notebooks full of his methods, and the golden ratio as a design rule for that painting appears in none of them. The claim is modern. You have likely heard that the chambered nautilus grows a golden spiral. The nautilus does grow a lovely logarithmic spiral, but measured shells generally do not match the golden one. The shape is real. The label is wrong. And you may have heard that these numbers can predict the stock market. Through the Fibonacci retracements drawn on trading charts, that belief is sincerely held by some traders, and there is no robust evidence that the Fibonacci levels themselves offer reliable predictive power beyond any other technical convention. Markets are not sunflowers, and they are not solving a problem of growth. How did the myth cloud form? Largely in the 19th century, when a German writer named Adolf Zeising published sweeping claims that the golden ratio governed beauty everywhere, in bodies, buildings, and art. The idea proved irresistible. One divine number threading through all creation, and lovely stories travel faster than careful ones. But the quieter truth is, we would argue, more beautiful rather than less. The golden ratio does not live everywhere. It appears reliably in certain systems whose growth and geometry happen to favour that proportion. In the sunflower and the pine cone and the leaves, arranging themselves around a stem to share the light. A number from a rabbit puzzle in a medieval Latin book, climbing out of the page and appearing. Verified. In the architecture of growing things. No myth is required. The truth by itself is strange enough to fall asleep to, and the story has one more turn. In the century just past, this same staircase of numbers left the garden and entered the machine. And the machines are humming quietly all around you tonight. Wherever you are as you listen, pause and take a small inventory of the room. Somewhere near you, almost certainly, there is a phone, perhaps a bank card in a wallet, a clock keeping time in some corner of the dark. This final chapter of the life is about the threads that run from a 13th century Pisan toward objects like these, and about drawing, carefully, the line between what Leonardo truly gave the modern world and what the modern world merely likes to say about him. Let us say the careful part first. Plainly, because the whole night has earned it. Leonardo did not invent the numerals. He did not bring them to Europe alone, for they had entered through Spain and through translations before him, and kept arriving through other hands after him. He did not create banking or bookkeeping. The history of each of those things is broad, many-peopled, and many-caused. What he did, and it is enough for one lifetime, was to give Latin Europe one of the fullest, clearest, and most practically convincing demonstrations of what the new arithmetic could do, at exactly the moment when the merchant cities of Italy were building the commercial machinery that would need it. He became one of the strongest bridges by which that knowledge crossed into the working life of the West. Not the only bridge, one of the strongest, and among the best documented, and the one whose book stood near the head of the teaching tradition that carried the figures into the counting houses. Through that tradition, the inheritance became invisible. Most of the everyday numbers you will see tomorrow, on receipts, on screens, on the label of a medicine bottle, are written in the positional system with 0 that his world called the Indian figures, and our world calls simply numbers. The paper machinery of finance that grew up in the Italian cities, the ledgers and balances whose distant descendants now live in every bank's computers, grew up hand in hand with the new arithmetic and the schools that taught it. No single ancestor owns that story, but stand in it at the year 1202. Look for the book that laid the method out for the Latin world with the greatest range and force, and you find the one written in Pisa. The modern computer has its own separate lineage, and honesty keeps us from drafting Leonardo as its grandfather. Your phone counts in binary, ones and zeros, a system with its own much later history. What computing shares with the tradition Leonardo championed is the broader principle of positional notation, the idea that a symbol's place determines its value, which is exactly how binary works, though its path there did not run through liber abaci, and it is the older idea of the algorithm, the step-by-step recipe for calculation, a word that traces back, as we heard, through the wider tradition of written reckoning to the name of Al-Khwarizmi. Every program ever written is a chain of such recipes, in that sense, of shared principles rather than a single family line. The world in your pocket and the customs house at BUGIA are distant relatives. The rabbit numbers themselves also found real work in the modern world, and the examples are verified and lovely. Computer scientists discovered that the sequence's way of growing makes it a natural tool for organizing information. There are searching techniques built on Fibonacci numbers, and a celebrated data structure called the Fibonacci heap, prized in the theory of efficient computation. Mathematicians proved that every whole number can be written in exactly one way, as a sum of Fibonacci numbers that never sit next to each other on the staircase, a small perfect fact called Zeckendorf's theorem. And separately, related ideas gave rise to schemes for encoding numbers, using the sequence, a development in the engineering of information. Even your travels can borrow the staircase, because neighbouring Fibonacci numbers sit almost exactly in the golden ratio, and because a mile relates to a kilometre by a ratio close to that same number, the sequence converts between them nearly for free. 5 miles is about 8 kilometres. 8 miles is about 13. A rabbit puzzle, moonlighting as a traveller's trick. 8 centuries on. The name, meanwhile, has become a small industry. Some of it earnest, some of it decorative. There are Fibonacci spirals on posters, Fibonacci poems, Fibonacci trading charts we have already weighed and found wanting. And in Pisa, in the 19th century, the city that once granted him £20 a year raised a statue of him, a marble scholar in robes, holding a book. The face is an invention. Of course, no one knows the face. The statue is a portrait of a reputation, and by now you know the difference between a reputation and a man, because that difference has been the quiet theme of this entire night. So let the inventory of the room finish itself. The phone, running its chains of recipes. The card, feeding a ledger kept in positional digits. The clock, dividing its hours. None of these objects knows his name, and none of them needs to. He spent his life making a difficult art so usable that it could disappear into ordinary hands. It disappeared so well that European scholarship needed 600 years to go looking for the men and books behind it, and to find, near the front of that long procession, a merchant's son from Pisa. And now, with the whole story told, we can stand back and look at the life entire, one last time before we let it rest. 800 years ago, a boy stood on a dock in Pisa watching men count. And tonight, the way of counting he championed is everywhere, while the man himself is almost nowhere. That is the strange, beautiful equation this life leaves behind. And it does not balance the way fame usually balances. Think of what we actually hold of him. A few sentences of autobiography, shorter than this closing chapter, a payment decree with his name spelled in official Latin, a handful of books that survived by threads, one of them by a thread so thin it nearly snapped. No face, no grave, no letters from friends, no anecdote. By the ordinary measures of memory, history very nearly lost Leonardo of Pisa, measured differently, though, and few working lives of his century reach so directly into yours. Every time you read a price, check the time, or glance at a number glowing on a screen in the dark, you are using the art he spent his life teaching, in the form his tradition helped give it. Perhaps the truest way to remember him is not as the genius of the rabbit puzzle, which was never really his, and which he never claimed, but as something rarer and harder, a carrier, a man who crossed between worlds that mistrusted each other and came back holding knowledge, patiently learned, patiently compared, patiently taught, asking no monument except that people use it. The scholars of India shaped the numbers. The scholars of the Islamic world refined and carried them. Many hands then bore them into Europe, through Spain, through Sicily, through the translators. Leonardo became one of the strongest of those carriers, and the crowds crossing after him wore his name away, and the knowledge held anyway. It is holding tonight, so we end where the records end, and where tonight began, with the decree of 1240, the discreet and learned Master Leonardo, honoured by his city for teaching it to count. Somewhere beyond that sentence, in years no document reaches. An old man in Pisa closed a book for the last time. The harbour kept trading. The tower kept leaning. The numbers kept spreading. Ledger by ledger, school by school, century by century, out of Italy, across Europe, across oceans he never sailed, into machines he could never have dreamed, and finally into this room, where they surround you now, patient and silent, the way they have surrounded every night of your life, without once asking to be noticed. One pair of rabbits in a walled garden. This month plus last month, forever. A simple rule, patiently applied, building something vast. He taught it to Europe as arithmetic. His life teaches it back to us as something else. Small things compound. A father's summons. Nameless teachers in a harbour town. One book, copied by hand, from city to city. And 8 centuries later, the whole world counts the way a Pisan merchant hoped it would. If this journey earned a place in your evening, there are more forgotten lives waiting here, each told slowly, and told with care. And if one thought stays with you as the lights go down, let it be the smallest and strangest fact of the night, that the numbers you least think about were carried to you across 1,000 miles and 800 years, by a man whose face no one remembers. The harbour is quiet now, the ledgers are closed, and somewhere on a library shelf, a manuscript is sleeping, 800 years old, and in no hurry at all. It waited 6 centuries for the world to open it once. It can wait for morning. Good night.